Alrighty, so it says lesson number 4. I stole this off of the physics teacher from the internet, so I think it might even be credited there at the bottom there. Says, the big misconception, what's the big deal? Many people have known Newton's first law since 8th grade or earlier and have prompted with the first few words. Most people could probably recite the law word for word, and that's the object arrest, stay arrest law. And what is so terribly difficult about remembering that F equals ma? It seems to be a simple algebraic statement for solving story problems. In fact, you could argue that it's a law. Well, it's called Newton's second law, right? It's a law. It helps us predict. The big deal, however, is not the ability to recite the first law, nor to use the second law to solve problems, but rather the ability to understand their meaning and to believe their implications. And I'm going to add one more thing, and to apply to new situations. Take what you know and apply it to a new and novel situation. While most people know what Newton's laws say, many people do not know what they mean or simply do not believe what they mean. And we actually saw that yesterday. I asked you the question about the bug hitting the windshield, and a good number of you, and same with the other class, the afternoon class, a good number of people said that the force in the bug was greater because the bug gets smucked. Are the forces unequal? No, they are equal. Why then does the bug get smucked? He's got much smaller mass. Right? And smaller forces affect smaller masses. Exactly. Small forces don't affect big masses. Cognitive scientists, or scientists who study how people learn, have shown that physics students come into physics class with a set of beliefs which they are unwilling or not easily willing to discard, despite evidence to the contrary. These beliefs about motion, known as misconceptions, hinder further learning. Okay? They slow it down. You have this set belief that you're not willing to adapt or to change. Why do you think that is? Humans are stubborn. Would you say, I might be stretching it here, I might be out of line, but would you say teenagers are more stubborn to change? Maybe some, I don't know. I would say that older people, and I'm not going to say like myself, are maybe resistant to change as well. I think, you know what, I'm going to take that back. I think there's a wide swath of age range that are resistant to change.
Just stubborn people.
Just stubborn people. I'm going to go with that, sure. Okay? So my job is to sort of identify those misconceptions and try to convince you, well, that you're wrong. Your job is to recognize that, well, you're wrong, and to say, oh, well, yeah.
I'm not wrong.
Yeah. Right? Now, is that to say that all teachers are always right? No, of course not, right? We're trying to challenge your ideas, and, you know, maybe 200 or 300 years from now, maybe we will be proved different. Aristotle, he's one of the most famous philosophers in the world, right? He was wrong over and over and over again.
You just didn't try him.
Well, unfortunately, he didn't do, like, you know, experiments. He just kind of thought about stuff. It's the way I interpret it. Anyway, so these beliefs about motion hinder further learning. The task of overcoming misconceptions involves becoming aware of their misconceptions, i.e., recognizing you're wrong, considering alternative conceptions or explanations, making a personal evaluation of the two competing ideas, and adopting a new conception that is more reasonable than the previously held misconception. In other words, replacing it with what you've been, you know, once you've been convinced, okay, yeah, I guess I was wrong. Right? It's not easy to say that you were wrong. It isn't.
I thought I was right.
Well, it's natural, right? It's no big deal. Yeah. This process involves self-reflection to ponder your own belief systems, critical thinking to analyze the reasonableness of two competing ideas, and applying that law of parsimony. And sometimes the law of parsimony gets in the way because what is simple might be your preconceived notion when it's not actually true, right? And evaluation. Select the most reasonable and harmonious model which explains the world of motion. Pretty big words in there. Self-reflection, critical thinking, and evaluation. While this process may seem terribly complicated, it's simply a matter of using your noodle, your brain. Okay, so there's your philosophy for the day. The most common misconception is one which dates back for ages. It is the idea that sustaining motion requires a continued force, and I really need to put some spacing in here. The misconception has already been discussed in previous lessons, but will now be discussed in more detail. This misconception sticks out its ugly head in a number of different ways and at a number of different times. As you read through the following discussion, give careful attention to your own belief systems. In other words, think about what you know or what you believe, and be willing to adapt. View physics as a system of thinking about the world rather than information that can be dumped into your brain without evaluating its consistency with your own belief systems. Newton's laws declare loudly that a net force, an unbalanced force, causes an acceleration. Forces cause accelerations. Do you need a force to keep something moving? Only if there's friction. The problem is there's always friction. Right? That's the problem. In the understanding part. To test your own belief system, consider the following question and its answer is seen by clicking the button. Obviously, you have a piece of paper and not a button. Are you infected with the misconception? Let me vaccinate you with some knowledge. Two students are discussing their physics homework prior to class. You guys probably do that all the time. Yeah. They are discussing an object which is being acted upon by two individual forces, both in a vertical direction. So here it is here. The free body diagram for the particular object shown at the right. Now, I haven't given you instruction about free body diagrams yet, but it's kind of fairly obvious from what this picture is, right? We got a box, we got a force down, we got a force up. One is 20 newtons down and one is 20 newtons up. Okay? And I'm just going to make some more spacing in here for myself because I'm finding it hard to read. During the discussion, analytical, pause for laughter, suggests to her friend know a formula. Thanks, Riley. I should have put on Riley's report card. Riley always laughs at my bad jokes. Thanks, Riley. Analytical suggests to know a formula that the object under discussion could be moving. In fact, Anna suggests that if friction and air resistance could be ignored because of their negligible size. What does the word negligible mean? Small, so small you don't need to worry about it. The object could be moving in a horizontal direction. According to Anna, an object experiencing forces described at the right could be experiencing a horizontal motion as described below. So she says analytical. Anna says this one could be moving. Could be. Not must be. Could be. Noah formula objects, arguing that the object could not have any horizontal motion if there are only vertical forces acting on it. He's saying it cannot be moving sideways if there's only up and down. Could not. Noah claims that an object must be at rest, perhaps on a table on a floor. After all, says Noah, an object experiencing a balance of forces will be at rest. Who do you agree with? I will let you think about it. Do you agree that one of them has to be wrong? Could they both be wrong? I guess that's true. I guess it's A and N, right? So Anna says it could be moving. And Noah says it must be at rest. He says it must be. She says it could be. Those are two different things. Noah says it must be stationary. It must be at rest. It must be not moving. That one. Anna says, well, it could be moving. Okay? Right now. Right from that picture. That's all you've got is that picture to work with. Okay, so I'm going to ask you to vote. We have no clickers because it didn't make sense to get clickers out for one question. Okay? You got to vote. You can't. Okay? So, sorry? Two. Analytical or no formula? Who's right? Hands up. Analytical. Could be moving. Okay? Who says must be at rest? Two. Is the majority always right?
No.
No. That's been proven over and over again. Oh. Well, let's just read this here. Remember last winter when you went sledding down the hill and across the level surface at the local park? Apologies extended to those who live in warmer climates. Obviously not us. We know what tobogganing is, right? You know, who's been to Durston Hill? Yeah, I haven't been there for a long time. I hear they've kind of, to Durston Hill, I hear they've kind of made it not as dangerous.
Oh,
It's so much fun. It's my
it's fun when it's dangerous.
Yeah, I don't think I have. Maybe I want to. Yeah, it's a lot of work to get back to the top, though.
Yeah, it is.
Yeah.
There's so much.
Especially if you have a foot that's like really big donut ones. Oh.
Imagine a moment there is no friction. We're going to answer this question. There is no friction along the level surface from point B to point C, and that there is no air resistance to impede your motion. How far would your sled travel, and what would the motion be like?
Keep going forever.
You'd keep going forever. Why? Objects in motion stay in motion, right? So the guy on the sled here he is right here, right? Once he gets to the bottom of the hill, if there's no friction or air resistance, he's just going to go forever and ever and ever until he runs into a tree. You would not. Once you hit flat, you'd be accelerating down the big Durston hill, but once you got flat, then it would be straight across, right? Most students I've talked to quickly answer. The sled would travel forever at constant speed. You guys all get that. You see that. Without friction or air resistance to slow it down, the sled would continue in motion with the same speed and in the same direction. The forces acting upon the sled from point B to point C would be the normal force, which we haven't talked a whole lot about, I get that. The snow pushes up on the sled, and the gravity force. See the diagram to the right. Well, in fact, it's this one right here, right? So we've got normal force, which is up, which is the ground, the reaction force, and you've got gravity down. Are they balanced? Just making some spacing here. They are balanced. These forces are balanced, and since the sled is already in motion at point B, it will continue in motion with the same speed in the same direction. So, as in the case of the sled, and as in the case of the object which Noah and Anna are discussing, an object can be moving to the right, even if the only force acting upon the object are vertical. Forces do not cause motion. Forces cause acceleration. So who was right? Anna is right. Okay? It could be moving. Could it be at rest? It could be. And that's the difference between the two. Noah said it must be at rest. But if he said it could be, then they both would have correct. Does that make sense? Yeah? I don't think that there's too many of you that I have to sort of work much harder at that. I think you get it. Okay? It could be at rest or it could be moving. Is that it? Is that the end of that? What do you guys have? Oh, no, it was a little bit more, right?
I just said yes to
Just to be agreeable. Newton's first law of motion declares that a force is not needed to keep an object in motion. Slide a book across the table and watch it slide to a rest position. The book in motion on the tabletop does not come to a rest position because of the absence of a force. Rather, it is the presence of a force. That force being the force of friction, which brings the book to a rest position. In the absence of a force of friction, the book would continue in motion with the same speed and direction forever, or at least until the end of the tabletop. A force is not, I'm going to get a highlighter. A force is not required to keep a moving book in motion, and a force is not required to keep a moving sled in motion, and a force is not required to keep any object, horizontally moving object, in motion. Right? Why do we need to keep pushing on things to keep them moving? Because of our arch nemesis, friction. That's why you slow down. It's not because of the absence of a force, it's because friction is omnipresent, forever present. Alrighty, so to be able to do these types of problems, you need to be able to draw a proper picture. So we need to spend a little bit of time drawing what we call free body diagrams. So I'm going to spend the next 20 minutes or so explaining these to you, and then I'm going to give you a chance to practice. Okay? So free body diagrams, otherwise known as FBDs, are simplified representations in a problem of an object, the body, and the force vectors acting on it. Vectors. Yeah. The body is free because the diagram will show it without its surroundings, i.e. it's free of its environment. And it also helps those of us that are not very artistic. This eliminates unnecessary information which might be given in a problem. Let's take this figure to be a pictorial representation of a situation, a sled on snow with horses pulling it. First, we represent the sled, which is the body of our problem, as a really simplified figure, a square resting on a flat surface. So there it is there. Do you have that? You do. Now, some books, some professors will argue, some teachers will argue that you should not have the flat surface there because that's not free then. You're including the floor. I'm okay either way. Okay, I think at this stage it's probably okay. I mean, even at later stages, right? I mean, if you understand what's going on, it's not that big of a deal. It's only people that are sort of those, want everything perfect kind of thing, technically. In this tutorial, we will review some of the main forces that you will encounter in physics and discuss their contribution to an FBD. So, the first one, because it's everywhere, is gravity. The first force we'll investigate is that due to gravity, and we'll call it the gravitational force. We know that acceleration due to gravity, if on Earth, is approximately 9.8 meters per second squared. The force by Newton's second law is Fw is equal to mg. Okay, which is really just F equals ma, where the acceleration is gravity. That's all it is. Okay? Where g is the acceleration due to gravity and m is the mass of the carriage. Let's add this to our diagram. So you should have that over here, right? So it always is drawn down. I call it the weight force, Fw. Others might call it Fg. You'll see it 2 or 3 different ways in different books and things, right? But it basically means the force of gravity. Note that the force vector labeled Fw or Fg points downward, as this is the direction which gravitational force acts. Is it always straight downwards?
No.
Always. Gravity is always down. Almost. Note that this force is commonly called weight. This weight is different from our everyday use of the word weight, which is known in physics as mass, which is why I have the bathroom scale to measure it. Because really, when people say, how much do you weigh? I like to say, oh, something must be broken because I don't weigh 100 newtons. About 825 newtons. That is my weight, because that is the force of gravity. I got this on the shelf in the Leonard store. I didn't go very well. The normal force. Normal force is one that prevents objects from falling into whatever it is that they're sitting upon. It is always perpendicular to the surface. Highlighter. Always perpendicular to the surface with which an object is in contact. Always perpendicular. For example, if there's a crate on the floor, then we say that the crate experiences a normal force exerted by the floor, and because of this force, the crate does not fall into the floor. The normal force in the crate points upward perpendicularly to the floor. So in other words, if it was this one here, then the normal force would be up, like so, and we label it Fn. Sometimes, some weird books want to label it F, and then, have you guys ever seen this sign? You know what that means? The upside down T? Perpendicular. Yeah, F perpendicular. Okay? It's called the normal force because normal and perpendicular mean the same thing. I don't know who decided that. Doesn't sound very normal to me. The normal force is always perpendicular to the surface with which a body is in contact. For a body on a sloping surface, like say a ramp, the normal force acting on the body is still perpendicular to the slope. So the normal force here is not straight up, it's, again, perpendicular. See that? Perpendicular. Now, which way is gravity? Up here, these forces are balanced, is the word I'm looking for. Are these forces balanced? They are not. And what happens when the forces aren't balanced? It accelerates. Well done, right? It accelerates, which is why things slide down ramps. Awesome. Let's add the normal force to our FBD and represent the normal force with the letter Fn. So you guys don't have to draw that. I really should change that picture. Okay, now friction. Related to the normal force is the frictional force. The two are related because they are both due to the fact that the body is in contact with the surface. Whereas the normal force was perpendicular to the surface, the frictional force is parallel. Normal and friction are always perpendicular to each other. Okay? Friction is parallel to the surface. Furthermore, friction opposes motion, and so its vector always points away from the direction of movement. Now, here's the next level of knowledge for you. Something you've never seen before, I'm guessing. Friction is divided into two types of friction, static and kinetic. These are represented by FF with a further subscript S for static friction and a subscript K for kinetic friction. 99% of the time, you don't need to worry about that. If you're taking university physics, you might see subscripts like that. I don't worry too much about it. It just confuses the point. As its name suggests, static friction occurs when the body is not moving with respect to the surface. The word static means stationary at rest. It is the force that makes it difficult to start something moving. On the other hand, kinetic friction occurs when the body is moving, sliding. Rolling objects experience friction as well. Rolling friction is actually quite complicated, and we're going to assume in all situations that we're dealing with sliding friction. This is the force that causes objects to slow down and actually stop. Friction is usually approximated as being proportional to the normal force. In other words, the bigger the mass, or the bigger, like if I stand on my scale, how much friction is there if you try to push it? A lot. How come? Because I increased the amount of force down, which increases the normal force out, right? So by increasing the mass, you increase friction. The proportionality constant is called the coefficient of static or kinetic friction. The coefficient of friction. This is something new for you. Colin, you appear to be holding your paper up. Are you making notes on there? Like it's just okay. You just look unusual. The coefficient is represented as mu s for static friction and mu k. Can you see that little symbol? I might make it bigger for you. Can you read it on yours? It's mu. It's the Greek letter mu, and it looks like this. It's really just kind of a U with a tail on the front. And it's pronounced mu. Mu. M-U. Mu. Well, in English, we write it as mu. In Greek, they just write it like that because it's the letter. It's like our letter. Actually, I think it's the Greek letter M, if I'm not mistaken. Why they use it, I have no idea. The numerical value of mu depends upon the nature of the surface with which the body is in contact. We've added kinetic friction to our free body diagram. I watched an episode of Big Bang Theory last night, and this could be caused by a person pushing a crate on the floor, a child pulling on a wagon, or in the case of our example, the horse pulling on a carriage. We will label the applied push or pull with FA, applied force. Now that's just sort of a generic applied force. Could you have more than one applied force? Absolutely. You could call, if you had more than one, you could call them FA1, FA2, FA3. Or just F1, F2, F3 is fine too, right? Like there's no hard and fast rule about how to do that, right? FF is pretty much friction force. So there could be multiple applied forces. Tension. Tension in an object results if the pulling force acts on its ends, such as in a rope used to pull a boulder. So here, for example, we say that our carriage is being pulled by a bar, by the horse at its front end, and we can add this force to our FBD. And so we have, I think the original one had an FT. I'm not a big fan of that. I prefer just to call it FA, applied force. Okay? Now, look at that completed FBD. The vertical forces are balanced. What about the horizontal forces? Not one is greater. The applied force is greater. So what's this object doing? Be careful. Accelerating. It's accelerating. Exactly. What if it accelerates up to a speed and then it just continues at that same speed? Well, then that applied force would be equal, right? And that's usually what happens, right? When horses pull sleds or you push lawnmowers or whatever, you push hard to get it going and then you push a little bit less. Because no one wants to accelerate over and over again. You want to be walking at a comfortable, consistent, constant speed.
So are we also kind of drawing into scale?
Yes, exactly. I'm glad you brought that up. So the length of the vectors, and this goes back to the vector stuff we talked about, the length of the vectors matters. Okay? So like if the diagram, if it says that it's accelerating, should your FA be considerably larger than your FF? Yeah, it should be, right? Now, am I going to get out my ruler and measure? No, I shouldn't have to, right? If it says it's accelerating, make it like twice as big. Like it doesn't have to be to scale, but it should be proportional. If it's bigger than the friction force, make it obviously bigger. If it's supposed to be equal, make it within plus or minus 2 millimeters, right? You don't need a ruler, just eyeball it. Okay, are you ready to do some? Probably. Example number 1, the sled. The child next door wants to take his German Shepherd named Spot for a ride on a sled. Good luck, dogs don't like riding on sleds. He chases Spot, who's running away while dragging his sled behind him. What forces are acting on the sled? Well, we discussed gravity, normal, friction, push or pull. Let's see if they come into play here. Let's consider each of the above forces in turn. Since the question does not state otherwise, we will assume that it's all happening on Earth. Fairly good assumption. So gravity is a force acting on the sled, and the gravitational force Fmg, or Fw, points downward. So let's draw that in. Fw. Now, some people like to draw the forces emanating or starting at the center of the object. Some of them like to draw it from there. You know what, I don't even know. I just draw. So sometimes I probably do it both ways, so it doesn't matter. The sled is being dragged in the ground, which we can take to be another surface. This surface exerts a force on the sled, preventing it from falling into the ground. Thus, there is a normal force. Oh, that's not good. Should those be balanced? Yep. Do we have to get out a ruler and measure them? No. There you go. This object is moving, but those forces are balanced, right? Fn. Because the sled is in motion and the surface with which it is has contact is not frictionless, then there is kinetic friction. Now, does it have to be to the left? No, it does not. Although we tend to live in certainly here in the West, North America, we kind of tend to view things going from left to right because we read that way. So generally, friction force is usually drawn pointing left, but it doesn't have to be. Ff. Now, we don't know how long it should be, though, right? So we'll just ballpark. Yeah. I think China. I think. Yeah, like they read from God. I think so. Hey, man, it's a big world out there. So there's a place to drive on the other side of the road. Oh, well, how's that any different? Does it? The child pulling on the sled. The child is pulling on the sled, so there is a pull force, F pull or Fa. The pull may not be parallel to the ground, but it may be at an angle. So it could be like this, or it could also be, we don't know really. Could be like this, right? And we don't actually, no, it would have to be actually what? For it to accelerate, it would actually have to be bigger, wouldn't it? Yeah. So it could be at an angle, or it could be flat. We're not sure in this situation because they haven't given us any information on that. I don't care right now. That would be right. Well, I mean, I guess technically, seeing as they haven't given us an angle, I guess you would have to assume that it's flat. You'd have to, right?
Oh, I'm so hard.
Yes, excellent, Colin. Colin's saying that if you're pulling it, sort of lifting it up at an angle, would you reduce friction? And you're bang on. We're going to get to that. You're like Nostradamus, predicting the future. Oh, that would be labeled with a FA. They're all capital S because they're forces, and then the subscript tells you what kind of forces.
Will we get marks off if we put a lower? Yeah.
Probably no. But they probably this convention. Okay, example 2, Dot and Spot. Spot, the German Shepherd, is being walked by his best pal. Dot beside his cat. I didn't make this up. Actually, Dot is pulling Spot across the ice rink and disturbing the neighborhood hockey game. What are the forces acting on Spot? Again, taking place on Earth. So we've got gravity, weight force. Hang on. Spot is on the surface of the ice. The ice is exerting a normal force. Let's deal with these ones first. We assume the ice is frictionless. Now, you have to sort of get good at reading questions. If it says polished surface or something that sort of implies no friction, then that's what they mean. So there is no friction. We assume ice is frictionless. Right? The push or pull may be misleading. While it's true that Spot is being pulled along by Dot, this is not the force acting on Spot. This is because God is actually pulling on the rope in turn through its tension exerts a force on the spot. What they want you to do is they want you to do this and call it FT. I say whoop-de-doo, I don't care, FA. Because really, who cares what it's labeled? Now, is that object accelerating? Is it moving? Can you say it must be moving? You can. How come? Because they're unbalanced forces, which means it's accelerating, and if it's accelerating, it must be moving. King Kong's pendulum. You've seen the King Kong movies? I remember watching it in 1977.
And they're making a new one.
Yeah. Skull Island, I think, right? Ah, King Kong's a classic story. I think the original movie was like from the 30s. It was some pretty bad special effects. Good for back then, yes. While climbing the Empire State Building, King Kong peeks into one of the corporate windows and sees a poster with Tarzan swinging from a vine. Our furry friend decides he'd much rather be swinging from vines instead of hanging outside skyscrapers. When King Kong is swinging from a vine, what forces are acting on him? We assume King Kong has traveled to the jungles on Earth, so he still experiences Earth's gravitational force. So, as always, weight force. The overgrown gorilla is not in contact with any surface, so there is no normal force. And that's the point of this example. Okay? Again, he's not in any contact with any surface, so neither static, there's no friction. So what's holding him up? Yeah, so this time you probably should call it tension. Is it just another form of an applied force? Absolutely. Would I mark you wrong if you put FA? No. But it's being applied. I mean, yeah, it usually is, I think. I don't know why. I don't know why these conventions exist. Now, if he's actually swinging like this, do we have to show that? Because we're only drawing the forces. You don't show an arrow for motion. You only show arrows for forces. Is that what you were asking, Kat? No? Oh. Oh, air resistance. Now, if he is swinging and you could draw a little bit of air resistance. I mean, it doesn't say, right? I guess you could. I guess that would be F. Technically, it would be like F air, maybe. I mean, at some point here, you got to sort of, right? It's all about your subscripts. I don't care. Technically, air resistance is a friction. I'm not going to draw. I'm going to assume it's. Would there be? Yeah, I guess there would. That's a great question.
So that's all you put?
Yeah, that's all you put. I would have to assume so. A good question would be, could you kick a football just as far in a smoggy Chinese city as you could in... I think they're out of business now, aren't they? Maybe they did that one, I don't know. I don't think they're on the air anymore. I think his mustache grew so big you can already see his face. Okay, last one, then I'm going to give you a chance to try some. Our furry friend King Kong has had enough of monkeying around. Return to the Big Apple. Once again, he's up to his tricks with the Empire State Building, only this time he's taking the elevator. While he's riding to the top of the building at a constant speed, what forces are acting on him? Well, it would be gravity and a normal force. And would they be balanced? Yes. He's rising, he's moving up at a constant speed, and so they are balanced. He's already moving. This is the question you asked me about half an hour ago, Pat. Right? The forces are balanced because he's rising at a constant speed. Okay. I think I've given you a pretty good idea of how to do these. Let's try some for fun.